Okay, so hello everyone. This is going to be the third video for this semester. This is going to be on electric potential and electric potential energy. And again, this is a series on learning from examples. Okay, so let's look at problem number one. It takes 20 joules to move an electron from location A to location B. Determine the potential difference between location A and location B. So here, what we want to know, what we want to look at is the relationship between the potential and the work done required to move from A to B per unit charge. So whatever charge that you're moving, which is going to be just Q, in this particular case, we actually have the charge of the electron to be the charge of the electron, which is 1.6 times 10 power of negative 19. Okay, so on the other hand, we have the amount of energy, right, which is going to be 20 joules. So 20 joules. So once we have that, what we will find is that the potential difference between those two locations are going to be 1.25 times 10 power of 20 volts. Okay. All right. So just to bear in mind that when we talk about potential, it's energy, which is in joules, and then per unit charge. So another way of writing this is actually saying potential is equals to 1.25 times 10 power of 20 joules per coulomb. This is another way of writing it. All right. Okay, so moving on to problem number two. It says here, determine the electric potential 20 centimeters from a positive 2 microcoulomb point charge. Okay, so imagine if you have a point charge, and it has a charge of positive 2 microcoulomb. Then what you will have is actually a potential. As you go further and further away, you actually have some amount of potential. And let's take the position of R. So this is the distance R. If we were to find the potential at R, we simply find KQ over R. Okay? So here it's important to note that K is just equal to 1 over 4 pi epsilon naught, which is not a problem. We just use 9 times 10 power of 9. The Q is actually the source. Okay, so the source here is actually the positive 2 microcoulomb. So this is the source. And then R is just the distance from it. So then what you're left with, if I substitute the values, I will have V at R equals to 20 centimeters. Okay, I will have 9 times 10 power of 9, and then I have 2, so positive 2 times 10 power of negative 6 over over 0.2. Okay, and that tells me that the potential at R equals to 0.2 meters is simply 90 kilovolts, or we can also write 90 kilojoule per coulomb. That's another way of writing it lah. Right? Okay, moving on to problem 3. Let's look at this question. A 0.2 millicoulomb charge moves from R equals to 0.5 meters to R equals to 0.2 meters from a positive 2 millicoulomb test charge. So if we were to just draw it out, I will have positive 2 millicoulomb, and let's say we have some distance, R equals to 0.2, and then R equals to 0.5. So initially the charge is here, so it's going to be positive 0.2 mc, and then it's moved to here, final position. Again, I have positive 0.2 millicoulomb, and I want to determine the work done by the 0.2 millicoulomb charge. Well, if it was up to the charge, they're both positives, so their forces is actually opposing each other. So we actually have to do work on it. So then we have to say that, okay, our work done by is equal to the negative of work done onto. Okay, so not much of a problem there. Okay, so then we ask the question, okay, how do I find the work done? We can find the difference in energy. So if we find the work done, it is just the difference in energy, electrical potential energy, and electrical potential energy is just KQQ over R. Okay, so what changes here is actually the R. So then I can change that so that I have KQQ, then 1 over R final minus 1 over R initial. Okay, so then what I can do is I can substitute the values. So the values will be 9 times 10 power of 9. The test charge is actually positive 0.2 millicoulomb. So millicoulomb is just times 10 power of negative 3. And then I have big Q, which is the source. That's just going to be positive 2 times 10 power of negative 3. And then the final position is 1 over 0.2 minus 1 over 0.5. Okay. So then what I'll have, if you key that into your calculator, is I'm going to have 10.8 kilojoule. That's the amount of energy needed to move the object from the charge from R equals to 0.5 to R equals to 0.2. Okay, so if I were to find the work done by, I would actually need to put that as negative 10.8 kilojoule. Okay, so my final answer here is negative 10.8 kilojoule. Okay, so moving on to problem 4. Here we have a system of multiple charged particles. Okay, so a system of charged particles consists of 2 microcoulomb charged particle and a negative 3 microcoulomb charged particle separated by 20 centimeters. So if I were to just draw it out, I'm going to have 2 microcoulomb, then I have 3 microcoulomb negative. Okay, and their separation is actually 20 centimeters. Determine the electric potential at the midpoint between them. So if I were to find the midpoint somewhere here, I would actually see that this is actually 10 centimeters. This is going to be 10 centimeters as well. Okay, so the good thing about potential is that they're not vectors. They are not vectors. V is not a vector. Okay, but it does work on the idea of a sink and a source. So a sink is like, if you have a positive charge, it's going to be like a hill. So if I put a ball, it's naturally going to come down. And then if I have a negatively charged particle, it will act more like a hole. If I put a ball, it's going to be coming down. So you have to preserve the positive and negative charge. So if I were to find the electric potential, I'll just call that V net. I will simply just add up all the potential. So which means I'm going to add the potential from the 2 microcoulomb plus the potential from the negative 3 microcoulomb. And since it's just KQ over R, I can take out the K. I will have 9 times 10 power of 9. And then Q is just 2 times 10 power of negative 6. And the distance between them, between the midpoint and the 2 microcoulomb charge, is 10 centimeters, which is 0.1. Then I'll just add negative 3 times 10 power of negative 6 over, again, 0.1. Okay, this will yield a final answer of negative 90 kilovolts or negative 90 kilojoules per coulomb. Okay, which makes sense. If I think about it, I have a sink, sorry, I have a source, which is, let's say, 2 meter 2, what the unit is 2, right? Then I add with a sink which has a depth of 1. What I will get is actually a sink with a depth of 1. Sorry, a source depth of 3, and then I'll have 1 because 2 plus negative 3 is equal to negative 1. So that's why I have a negative value as the net potential. Okay, so now we move on to problem 5. Okay, a system of charged particles consists of 3 positive 2 microcoulomb arranged in the corners of an equilateral triangle of sides 20 centimeters. So let's just assume I have okay, let's see if I have equilateral triangle. Okay, let's just assume that's an equilateral triangle. And then I have, let's say, Q1 here. I have Q2 here. I have Q3. Then your potential energy is simply going to be K Q1, Q2, then the distance between 1 and 2, plus Q2, Q3, then the distance between 2 and 3, plus Q1, Q3, then the distance between 1 and 3. I would like to emphasize that this corresponds to these two. As you can see below, we have 2, 3. Then I have 2 and 3 at the top as well. Okay, but because Q1 is equal to Q2, which is equals to Q3, I can quite simplify and say that U is equals to K Q square over R. Okay, and bear in mind R12, this length, is the same as this length, which is the same as this length. So then I have R12 plus, R12 equals to R13 equals to R23. Okay, so I'll just be adding it 3 times. I can just multiply it by 3. So then my U is equal to 3 times 9 times 10 power of 9, and then multiply by Q square, which is just 2 times 10 power of negative 6 squared. Then I have 0.2, the distances between them, which is 0.2 meters. So then what I'm left with is that my U is going to be 0.54 joule. Okay, and that's the potential energy of the system. If you provide it with this amount of energy, it will break apart. Okay, so moving on to problem 6. We have this question. A system of charged particles consists of 3 positive 2 microcoulomb arranged in the corners of a right angle triangle of sides 20 centimeters. Okay. Determine the electric potential in the center of the hypotenuse of the triangle formation. So let's first draw a right angle triangle. Okay, that's a right angle triangle, and then I will have 3 circles here. I will have all positive 2 microcoulomb, positive 2 microcoulomb, and then positive 2 microcoulomb. And then what I want to find is I want to find the potential in the middle of the hypotenuse. Okay, so it's been established that the sides of this right angle triangle is 20 centimeters. Okay, which is nice because then it actually forms a square technically. Oh no. Okay, it actually forms a square. Okay, then we can figure out the distance between here and here. Okay, so if I just take the square root, so let's call this length to be L. Okay, it's the same length as this one. This is going to be L, this is going to be L as well. Okay, so this L is simply going to be the square root of 0.2 square plus 0.2 square, and this L is actually approximately 0.141 meters. Okay, so if I were to find the potential at that midpoint, I will have to just add up all the potential. So if I were to find V net, I simply need to add up V1 plus V2 plus V3. Okay, so then my V net is just K and then Q1 over R from R1 plus Q2 over R2 plus Q3 over R3. Okay, so again, these charges are all the same, the distances are all the same, so I can quite easily say that it's going to be 3K Q over R. Specifically, this is not R, this is actually L. Okay, so I'll just correct that, Q over L. Then I will have 3 times 9 times 10 power of 9. Then my Q is just positive 2 mu. Mu here is times 10 power of negative 6 over the L that I calculated, which is 0.141. Okay, so then I'm left with, let's see, I'm left with 3.83 times 10 power of 5 joules. Sorry, joules per coulomb. Okay, and that's my V net. That is my V at the center of the hypotenuse of the triangle formation. All right, and that is all for this video. Thank you very much.